Hello, everyone. We are Group 2, and we're going to be presenting an analysis of convolutional 2D knowledge graph embedding. Our team is composed of Gerrit, Krot, myself, Alejandro, Yaber, Llanos, and Calvin Now. Next slide, please. To start off, we're going to have to be talking a little bit about what are knowledge graphs, as these are very important within the learning task that is presented in Detmers et al., which is the paper that we're reproducing. Knowledge graphs are structures or graphical structures that model data that have relationships between two different entities that are called objects and subjects. And the learning task associated within this problem using knowledge graphs is something called link prediction. Link prediction, what it tries to achieve is how we can find out the relationship between one object and one subject that we don't know about within a knowledge graph that is already there, and taking into account the other relationships within the knowledge graph. These learning tasks on link prediction are usually used in social media, spam detection, and other areas where we need to predict those relationships. Next slide, please. An example of a learning task within link prediction can be seen in this small figure. As we can see, we have three nodes that we can call all objects or subjects, depending on the type of relationship that we're seeing. And we can see that the node on the top right we can call A, the one on the bottom we can call B, and the one on the far right we can call C. We can see that between A and B there is a relationship of they are friends. We can see a relationship between A and C that also says they are friends. So link prediction would be trying to define, based on the previous relationships between the objects and subjects, what would be the relationship between B and C? Can we say they are related, or they are friends, or another type of prediction?
Thanks for covering that, Alex. I'll pick it up from here. So after we have done link prediction, we can then look at our learning model, and this is a model presented by Detmers et al. And they advanced the idea of link prediction in the models that have been produced before by including a convolutional layer to increase feature expressiveness. As we've discussed before in class, convolutional models are really great because you can have an increased number of channels, and these channels can each learn a different representation of our feature space. And this can allow us to take advantage of increased feature complexity, which allows for a better model without having this explosion in memory requirements that's associated with fully connected layers. And as we've already gone over before in class, convolutions are very efficient, so we can do this and get a much more expressive, much more accurate model without running into memory requirements that we aren't able to accommodate. So from that, we got this idea of transfer learning. Since this model's much more accurate than previous models, we wanted to know, could we make it even faster than it already was and more and improve on it some more. So transfer learning is this idea of utilizing any knowledge resource to increase model learning and generalization for target tasks. In the context of this model, we wanted to use the weights that had been previously learned from another data set to initiate the dimensionally invariant weights within the network. And we wanted to see if this would reduce training time without a cost to accuracy. This was what our hypothesis was, is that it would reduce training time without a cost to accuracy. And in terms of what we would expect it to confirm this, is we would expect that both models would train in a fewer number of epochs to reach the same training loss. So that would be kind of an idea of like reducing the overall training time while achieving the same loss. And it would be contradicted if both of these models do not train in a fewer number of epochs, or if they trained in the same number of epochs and reached a lower performance at the end of training. And it would be unclear whether it was confirmed or contradicted if one of our models kind of supported our hypothesis and the other one contradicted it. So in terms of our experimental design, we had two data sets that we wanted to look at. One was a knowledge-based relation data set, sort of, you could think about, is Lionel Messi a player for Real Madrid, right? That could be like a knowledge-based relationship. And then word-based relationships, like, is this an adjective or not? And we wanted to train one model using a given data set, get the final weights for that data set, and then initialize the training of the next model using the weights from the prior learned data set. So as I kind of went over, we're gonna basically transfer the weights from one fully trained model to the beginning of another trained model with a new data set. And we're gonna maintain the hyperparameters over that training. And then we're gonna add an early stopping procedure in there based on the training loss of the model. And the idea here is we're gonna use training loss as a proxy for how much our model learned. So once the model reaches the same training loss as it would as if it was trained without transfer learning, we're going to stop model training. And then we're going to use some performance metrics, similar performance metrics to what the paper used, just to ensure that we actually do have a model that performs with similar accuracy to the one that was trained fully without transfer learning.
So as you can see here, we do in fact have results that show that transfer learning produces models with very similar accuracy to the Detmers et al. Paper and our reproduced results. They are very, very similar to our reproduced results. Most of our values are very slightly worse, but not more significantly than our reproduction was different from Detmers et al. So most of this can be chalked up due to some random initialization and other such factors outside of our early stopping procedure and the transfer learning. But what cannot be overlooked is the significant decrease in training time that we got as a result of the early stopping procedure and the transfer learning. It took the WorldNet model, the model trained on the WorldNet data set, only 243 epochs or 2 hours 44 minutes to reach the same accuracy and the same metrics as it took 1,000 epochs and 12 hours. And for the freebase model, it took only 37 epochs or 39 minutes, what took 15 hours and 46 minutes over 1,000 epochs previously. So it's clear that the effect of transfer learning in on Conv is improved model accuracy with less training time. In that if you were to run these models for even a little bit longer, the model accuracy would almost certainly improve a lot faster than with randomly generated initializations. This is surprising given that the two tasks, the data sets that the models were trained on, are mostly unrelated. WorldNet is world-based relations and freebase is knowledge-based relations, which don't have much overlap. The limitation of this implementation is that you need to run a model previously and have the initial data sets for transfer learning to work. And you need to know the fully trained loss value in order to implement a stopping procedure. Future work could address a stopping procedure based on a different metric, potentially based on accuracy or test results, but that might make the model run longer. But overall, transfer learning does appear to be very effective with the Conv model on the limited data sets presented. Put your questions in the comments.